Hello viewers, in today's class we are going to see about angular harmonic oscillator. So a simple harmonic motion can also be angular. In this case, the restoring torque required for producing simple harmonic motion is directly proportional to the angular displacement and is directed towards the mean position. So here torque is directly proportional to theta, the angle. So this can be written as torque is equal to the constant of proportionality is minus C. So C is called torque constant and theta depends on the angle theta. Now consider a rigid support, a string. This is a string. This is top end of the string where it is fixed firmly, and this is bottom end of the string where here also you have a load. So what you do is, this is the center part of this load. What you are doing is, the string is moved like this, it is turned. So when it turns an angle theta, if you just release your hand, it will come to the mean position, and because of the force exertion, it will go to the opposite side and start swinging, twisting around A and B. So this is the angle theta, and so torque is directly proportional to theta. So this can be written as torque equal to minus C theta, the constant of proportionality. C is the torque constant. So when you try to twist the string, say anti-clockwise by an angle theta, there is an opposite force. Okay, that's why we put a minus sign. Now we will see the derivation part of this angular harmonic oscillator. So we all know that torque is equal to R vector cross product with F vector. R is the radius, F is the force. So the unit for C. So in this case C, from this C is equal to, the unit of torque is, force is Newton, distance is meter, divided by theta. Theta is angle. So we are representing in terms of radian. So the unit for C will be Newton meter radian power minus 1. Okay. So the negative sign shows that torque is acting in the opposite direction to the angular displacement. That's what I told you. When you try to twist the string, this is string, say metallic string or some other string. When you try to twist, it moves on angle theta. There is equally an opposite force. So this is mean position. So it will start oscillating between A and B. And if there is no additional force, it will lead to damped oscillations. All these things we will see in the some other video. Okay. So first equation what we have is this equation, and we have a relation already we have covered in the earlier topics. Torque is equal to I alpha. Now I is the moment of inertia. And alpha is the angular acceleration. So now we have two relations. This from the basic definition or the basic principle that we have observed in this case. So torque is equal to minus c theta, and this one is an established result. Already we have studied in the earlier topics. So torque is equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. So therefore what we can do is, from this alpha, from this relation alpha, that is angular acceleration, alpha is equal to torque by I, where I is the moment of inertia. Now this torque can be replaced by, this tau can be replaced by minus c theta by I. This minus c theta is from this equation. Okay, this is second equation. Okay, now next, now we got already A is equal to minus omega square y. This relation we have discussed with the simple harmonic motion earlier. So A acceleration is equal to minus omega square y. This result we already got. So making use of this relation, now replacing y by theta. So in this equation y is replaced with theta. There what we discussed is when a particle moves, so you see a vertical displacement. So now here it is angular displacement. So y can be equated to theta. So y is replaced with theta, and A by alpha. There we have acceleration, linear acceleration. Here we have alpha. Alpha is angular acceleration. So these two things we are going to do with this basic equation. Y is replaced by the theta, this theta, and acceleration is replaced by angular acceleration. So therefore what we have is alpha, A is replaced by alpha, is equal to minus omega square, y is replaced by theta. That is alpha is equal to minus omega square theta. Okay. Now what is omega square? So omega, so this is nothing but alpha is equal to minus c by I theta. Now c by I is equal to alpha is here, tau by I, which is nothing but minus c by I theta. Therefore you can equate this alpha with minus c by I theta. That's what is written here. Now we have two relations, alpha is equal to minus omega square theta and alpha is equal to minus c by I theta. Okay. Therefore these two equations can be equated. This equation and this equation can be equated. So we have minus omega square theta is equal to minus c by I theta. So minus gets cancelled, theta also gets cancelled, and finally we have omega square is equal to c by I. So we have omega square is equal to c by I. Okay. Omega. Therefore omega is equal to square root of c by I. Omega is 2 pi f, which is equal to square root of C by I. F is the frequency. F is equal to 1 by 2 pi root of C by I. Okay. So this is the frequency. If at all you are interested in finding out the period, now I want period. So you can always find period using the relation T is equal to 1 by F. So 1 divided by frequency, this term, that is 1 by 2 pi square root of C by I. So now what will happen is 2 pi square root of I by C. This is time period. So time period is given by time period of simple harmonic motion. In this case it is angular, is given by 2 pi square root of I divided by C. You must remember any one formula is sufficient. Either you remember this equation or you remember time period. You can find out the other terms easily. So that's all about angular harmonic oscillator. So we have dealing with the movement of deviating at an angle, say theta, and because of that there is a restoring force, and we have equated the torque produced with respect to theta, and finally we have arrived at this relation. Frequency is equal to 1 by 2 pi square root of C by A, or in terms of time period, T is equal to 2 pi square root of I by C. So both frequency and time period depends on square root of C divided by I, that is inertia, depends on inertia in both the cases. That's all about angular harmonic oscillator. Thanks for watching. Nandri.